Okay, welcome everyone to the 128th meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Yorick Fuhrmann from the University of Warwick, and he'll be talking to us about modular fixed points and equivariant homotopy theory.
Okay, thank you very much. Thank you very much for the invitation. Just one question. Can you see what I just shared?
Yeah.
Yeah, very good. Thank
Yeah.
you. Okay. Yeah, so I'm going to talk about these modular fixed points, which are essentially some R-linear version of geometric fixed points. And so throughout my talk, G will be a profinite group. Sometimes I'll assume that the group is finite. I'll mention when I do that. But yeah, most things I'll say like in the first half of the talk will hold for profinite groups. And when I say things like subgroup, you should probably think open subgroup. And yeah, many of the things that hold for finite groups are formally extended to profinite groups. So yeah. And R is a discrete commutative ring. And I'll start by recalling what the category of Mackey functors is, which will be really important throughout the talk. So R-linear Mackey functor, that's what I'm doing here, are additive functors out of the opposite of the Burnside 1 category. So this is the Burnside 1 category, which I write omega G. I take finite G sets and then the hom sets are abelian monoids under disjoint union. I take spans of finite G sets. The hom sets are abelian monoids under disjoint union, and I can group complete that, and I get this category. And when I tensor the hom groups with R, I get this R linear gadget, which has the subscript R. And then I take R linear functors, and I take functors which are valued in R modules. So I do R module valued Mackey functors. Okay. And then in this category, I have a full subcategory, which is this full subcategory of cohomological Mackey functors. And they're defined by the property that a span of canonical projections, like here, is sent to multiplication by the index. So whenever I have such an inclusion of subgroups and such a span, I send it to multiplication by the index. Okay. And let me mention two important examples. So the first one is the R-linear Burnside Mackey functor, which is represented by the point, so by the G set G mod G. And yeah, if I want the R-linear version, then I tensor this with R. And this category of Mackey functors or of R-linear Mackey functors has a symmetric monoidal structure. It's given by Day convolution, and this functor is the unit for that structure. Okay, and when I take modules over this R-linear guy in just plain Mackey functors, and when I don't write a subscript here, I mean values in abelian groups. So when I leave the subscript away, that's just kind of Z-linear Mackey functors. Then I just get back Mac R of G. Okay, and then I also have another one, which is the constant Mackey functor. So it's got the value R on each G set. So for each subgroup. Sorry, not for each G set, for each transitive G set. So for each of these orbits, where H is a open subgroup of G, I have the value R. The restriction maps are identical, and the induction maps multiplied by the index. And yeah, there's different description of Mackey functors. So I'm talking about restriction and induction. These are encoded by the different legs of the span. So like the leg that is kind of the left leg encodes the restrictions, the leg that is the right leg encodes the inductions. And yeah, okay. And if I take modules over this guy, what I get is the category of cohomological Mackey functors. Okay, and that has already been observed by Thavenar and Webb in their paper, The Structure of Mackey Functors, which is kind of a classical one on Mackey functors. Okay, and let me go on and talk about equivariant spectra. So yeah, I will consider the infinity category of genuine G spectra. I will not say genuine anymore. This is what I mean. And there are very many different models for this, but yeah, one I can just like briefly write down is this category of spectral Mackey functors. And for that, we take functors out of the Burnside infinity category of finite G sets, of the opposite, and I take product-preserving functors which are valued in spectra. Okay, and so if you're not familiar with this Burnside infinity category, I'm not constructing it now, but if I take the homotopy category of that, then I get the effective Burnside 1 category, which is kind of the one I had before up to group completing the home sets. So yeah, I guess maybe to be very precise, I should write effective here. Yeah, but if you map to something that has group complete home sets or something like that, then we don't need to group complete. That's kind of the feature. Okay, and this category inherits a T-structure from spectra, and it has T-structure homotopy groups, which I can write down like that. So I have a homotopy group for each subgroup of G, and it's integer graded, and so that's what I denote by the superscript H, the subscript N, and I take the mapping space in G spectra from like the N shift of the infinite suspension of this G set G mod H and map into X, and then I take the pi naught of this whole mapping space. So when I write hom, I mean the pi naught of the mapping space. And what does this give me? I can look at the heart of this T structure. So I look at SPG, and then I write T heart because later I will talk about other hearts, namely hearts for weight structures. And I can include that into G spectra. And yeah, you probably know that this is equivalent to the category of just Z linear Mackey functors. Okay, and then what I can also do is I can look at the R linear Mackey functors, and I have like a forgetful functor to just Mackey functors. And so I get this composition, and this functor here I'll call H is the equivariant Eilenberg-MacLane spectrum. Okay. Right, so now I'm going to talk about different ways to promote my commutative ring, my discrete commutative ring to an equivariant spectrum. And there are like many different ways you could come up with. I'm just going to give you three. I'm not claiming these are all the ways to do it, but these three I can nicely relate to each other. And so the first one I want to do is what I write as HR sub G, which is defined as the inflation from the trivial group to G. And I just take the ordinary Eilenberg-MacLane spectrum and inflate it to G spectra. So this here is the restriction functor associated to the morphism that goes from G to G mod G. That's this inflation functor. And okay, I get the spectrum. And then I can look at the Eilenberg-MacLane spectrum of the two things I already mentioned. So I can look at the equivariant Eilenberg-MacLane spectrum of the constant Mackey functor. And I can look at the Eilenberg-MacLane spectrum of the R-linear Burnside-Mackey functor. And I drew them in a triangle. And the reason for that is I want to give maps between those things. And I should also say all of these spectrums here are commutative algebra objects of G spectra. Yeah, so they're already the ones on the right-hand side. So the constant Mackey functor and the Burnside-Mackey functor, they're already algebra objects in Mackey functors, and this Eilenberg-MacLane spectrum functor is Lux symmetric monoidal, and this inflation functor is symmetric monoidal, and HR is a ring spectrum, and so these are all algebra objects. And how do I give this map? So what I can do is I can look at HRG, and I can use the T-structure truncation, and I have a map in this way, and then this is equivalent to HAR. This has been observed by Greenlees and Shipley in a paper on equivariant module spectra. And then here I can give a further map to HR underbar, which just corresponds to the unit map from the R-linear Burnside-Mackey functor to the constant Mackey functor, and that would be the unit of Mac R T. Okay, so I have this map, and another way to obtain such a map is the following observation. So when I look at maps like that. So giving such a map is equivalent because the target is in the t-hat and my source is connective. So my inflation functor is right t-exact, so it preserves connective parts. And so sorry, that's not what I want to do. Sorry, I just mean the adjunction. So this on the left-hand side is inflated. And so I can just use the fact that it's a left adjoint. So this is equivalent to giving a map out of HR into the categorical fixed points, which is the right adjoint of inflation. Okay, and the categorical fixed points of that are just HR. So yeah, so the categorical G fixed points of such an Eilenberg-MacLane spectrum are the Eilenberg-MacLane spectrum associated to the sections for this group. Okay. And then I can give a map from HR to HR, which is just the identity. Right. And now I want to talk about the module categories over these algebra objects. So yeah, so the fact that I have such algebra maps gives me extension of scalar functors. But I also want to kind of motivate considering these categories by giving you some more equivalent descriptions of these categories, which yeah might speak to some people and they might not speak to some people, but it definitely makes the point that some of these categories have like some relations to representation theory, for example, or to equivariant algebra. So let me do that. Okay, so I get these extension of scalar functors from the ring maps above. Okay, and so what is this thing here? This category is also equivalent to what I call, I guess not I, but Kaledin calls DMAC. So this is what he calls derived Mackey functors. And this is not the derived infinity category of R-linear Mackey functors. This is something else, which I'm not going to go into the details, but another way to describe this is just product preserving functors out of the opposite of the Burnside infinity category into HR modules. So this means R modules in spectra. So this is kind of the most naive R linearization of G spectra, if you recall the spectra Mackey functor description of G spectra. And this has been shown by Patch, Correa, Sanders, and Wimmer in their paper on the spectrum of derived Mackey functors. Okay, and on the right-hand side, let me do the one on the bottom first. This really is now the derived infinity category of Mackey functors. Also shown by the three authors I just mentioned. And another way to describe this is a spectrum Mackey functor description as follows. So I take this omega RG gadget before, so this R linear Burnside 1 category, and I take product preserving functors out of the opposite into spectra. And then here, this now is the derived infinity category of cohomological Mackey functors. And another way to describe this is the category E-perm of GR. So this is the derived category of permutation modules. I'll talk a bit more about permutation modules, but yeah, so what they are is just free R modules on a G set. These are the permutation modules, and yeah, but that category is not abelian, so deriving it is not quite clear a priori what it is, but this is some derived version of them, and this is also equivalent to product preserving functors out of finitely generated GR permutation modules. So this really is now this is the one category of finitely generated GR permutation modules. So free R modules on a finite G set. And this equivalence, why do I write this? make some more space. So this, in the one categorical or triangulated case, this has been shown by Balmer and Gallauer. Okay. Right. What I want to do now is talk about geometric fixed points on these categories, and there are kind of three different cases we have to consider. So let me first recall some basic facts about geometric fixed points, namely for a subgroup of my group G. In the profinite case, I have to take a pro subgroup. There is a symmetric monoidal left adjoint geometric fixed point functor. And what I want to do is I want to take a geometric fixed point which land in spectra for the Weyl group. So this notation here, G double mod H is my notation for the Weyl group, NGH mod H. Okay, yeah, for many people this might be the partial geometric fixed point functor because they're used to geometric fixed points which are valued in just spectra. But if you want to take this one and then restrict to spectra, you kind of get what you used to. And it fits into this nice commutative diagram, which has infinite suspension functors from pointed equivariant spaces to equivariant spectra. And then this functor on the top just takes fixed points on equivariant spaces. So in particular, we have this property that the geometric fixed points of a suspension spectrum are equivalent to the suspension spectrum of the fixed points. So that's kind of why they're called geometric for X in pointed G spaces. Okay, and something I want to emphasize, which will be important later, is that if I take a normal subgroup, then this geometric fixed point functor is just a localization, namely it's the one that kills equivariant points of subgroups which do not contain my normal subgroup. I will make this precise. So it is the functor from SPG to a certain Verdier quotient, and the Verdier quotient is by the localizing tensor ideal generated by suspension spectra G mod H for H not containing N. And this is in fact equivalent to SPG mod N. Okay, so this is kind of killing off orbits of subgroups that do not contain N. All right, and so what do I do in the cases I already considered? So I'll write B for the moment for one of those three functors, or one of those three spectra, I should say, I mentioned. So either the inflation of HR or the Eilenberg-MacLane spectra of the R-linear-Burnside-Mackey functor or the constant Mackey functor associated to R. And what I always get is just like an induced functor on module categories. This is just so geometric fixed points are symmetric monoidal, and I get this induced functor on module categories, but I land in modules over this ring here. And so, so in some cases, this is already the correct target, namely for HR sub G. This is already the correct target because geometric fixed points behaves nicely with respect to restriction along a restriction along a group homomorphism. So it commutes with these inflation functors, and the geometric fixed points of this inflated spectrum are itself an inflated spectrum. And so up to equivalence, when I take a normal subgroup, this is again a localization. And this localization is, it's generated, the localizing tensor ideal is generated by kind of the analogous generators. So I take the free modules associated to the suspension spectra of subgroups which do not contain N. And Patch, Correa, Sanders, and Wimmer have shown that this is really equivalent to modules over the inflation of HR to G mod N. Okay. And why am I mentioning these functors? So Patch, Correa, Sanders, and Wimmer have used these functors on, which are kind of functors on derived Mackey functors under this equivalent description to describe the Balmer spectrum of derived Mackey functors. So these are actually functors that have been used, and this is kind of a nice perspective, I think. And so for the Burnside Mackey functor, we kind of run into a problem because the property I mentioned before is not true anymore. So let me give you an example. When I take the homotopy groups of the C2 fixed points, C2 geometric fixed points of H, A, Z, and so this is total geometric fixed points now. So this is a C2 spectrum, and I take total C2 geometric fixed points. This is also Patch-Correa, Sander, and Wimmer, is equivalent to Z mod X, sorry, ZX mod 2X. Okay, and the generator here lives in degree 2. And so what I do when I do the induced functor on module categories is I make this localization by this analogous localizing tensor ideal here. But the target, like this whole quotient, is in general not equivalent, provably not equivalent to this module category where I actually want to land. And so, yeah, so the naive thing kind of didn't work, and I can do the second most naive thing, which is kind of base changing back to where I wanted to land. Namely, when I do pi naught of the geometric fixed points of HAR, then I get AR back. And this works for all subgroups. And one can show this using geometric fixed points on Mackey functors, which have been considered, for example, by Hill, Merle, and Quigley. They've shown that they're preserving representables. And then Bloomberg, Gerhardt, Hill, and Lawson have shown that the pi naught of the actual geometric fixed points on equivariant spectra of some Eilenberg-MacLane spectrum agrees with these geometric fixed points on Mackey functors. And so what I get is a ring map, which is just the identity on pi naught, like that. And then I can look at the functor I had before. So I have this module category. I take geometric fixed points, the induced functor by geometric fixed points. I land in modules over this kind of too large ring. And then I base change back. So I land in this category. This is extension of scalars by alpha. And so by definition, this composition factors through kind of everything induced from proper subgroups. So it factors through this quotient I had above, but this quotient is kind of, it's too rich, like it's too large, and so I can base change back. Okay. And now for the Eilenberg-MacLane spectrum of the constant Mackey functor, I kind of have the same problem. So I'll give you another example in this case, which is I can look at the homotopy of the C2 to the n geometric fixed points of H. And so again, this is total geometric fixed points. So this is like a C2 to the n spectrum. And this is isomorphic to Z mod 2 polynomial ring. And X lives in degree 2. And this has been shown by Hill, Hopkins, and Ravenel in their famous paper on the covariant invariant. And so in particular, yeah, I don't get back the Eilenberg-MacLane spectrum of a constant Mackey functor, but also I see that the pi naught is not kind of what I wanted, so what I wanted to be. So also pi naught of this ring is not isomorphic to Z, which would be, yeah, what I want, which is kind of because Z is the constant Mackey functor for the trivial group. Okay, and so I'm asking the question, when is the pi naught actually the constant Mackey functor again? And that's the next proposition gives the answer to that, namely when I take a finite group and I take a p subgroup and I assume that p is 0 in my ring R, then I get such an isomorphism. Okay, and why is that the case? So you can do some computation in Bredon homology, or you use these geometric fixed points on Mackey functors I mentioned to arrive at a description of the K mod H sections of this ring. And here K mod H is a subgroup of the Weyl group. And what is this description? So I have a co-kernel of a direct sum of induction maps. And because I have the constant Mackey functor here, these induction maps multiply by the index. And the sum runs over subgroups of K which do not contain H. Okay, and so to kind of get the correct section, what I need is that all these indices are divisible by P. Because then they are then these maps are zero maps and my co-kernel doesn't kill the R on the right-hand side. And okay, I wanna briefly illustrate what that is the case. So when I take K and when I write the order of K as P to the K times A, so that P does not divide A, the order of L as P to the LB, so that P does not divide B, then this index here is P to the K minus L times A over B, and I assume for the moment that L is equal to K. Okay, which would be the case that this this index is not divisible by P. And what I can do is I can take a solo P subgroup of L, and then that has order P to the L, but because I assumed that L is K, that is P to the K, and so I know that that's already a solo P subgroup of K. But I assume that K is a P subgroup, so it's in the sub P of K. And so H itself is contained in some conjugate of this solo P subgroup. So for some X in K, which is itself contained in the normalizer of H. And then I know that H is equal to H to the conjugated by X inverse, which is contained in S, which is contained in L, but that's a contradiction because I assumed that H is not contained in L. Okay, so I see that these assumptions give me what I want, basically. And I also want to illustrate why I take P subgroups again, by just assuming that R is a field and assuming that it has characteristic P, so prime characteristic. And then I know by this description above that these sections here are either K or zero, depending on the indices on these indices here. Okay, and so if H is not a P group, what I can do is I can take K to be equal to just NGH and L some solo P subgroup of NGH. And then H is not contained in L. And so I know that P does not divide the index NGH of L and NGH. And this itself is then invertible in K. And then I get that this section vanishes, which I don't want because I want to map out of this for my base change morphism. And so the assumption that H is a P subgroup is important for this. So I have three cases. One case, I already land in the correct target. One case, I can base change to the correct target for all subgroups. And like my last case, the last case I discussed, I can base change, but only for certain subgroups, namely the P subgroups. Okay. And so the definition of my equivariant modular fixed point functor for G finite H a P subgroup P0 in R is just, I define it as the composition that that I had before for the Burnside-Mackey functor. So it just factors through modules over this one here. Okay, and then this map psi is here, identical on pi naught. Okay. So what you might wonder about is what happens if I choose a different ring map? In theory, I could choose any endomorphism of R once I computed the pi naught. And so many properties of this functor will hold for any choice of ring map. But there are some things which for which the choice of the ring map is important. For example, when I choose an R linear structure for these module categories that comes from an identity of R, then the only choice I'm left with to achieve an R linear functor for this modular fixed point functor is the identity on R. And also, what I'll talk about in a bit is the fact that Balmer and Gallauer have defined similar functors on derived permutation modules. This is kind of what motivated this whole story. And I later identify my modular fixed point functor with their modular fixed point functor. And for that, it's also important to choose the identity. Okay, so I want to mention a few properties of this functor, of these modular fixed point functors. So yeah, the first one is relatively immediate, at least the first part. It's a symmetric monoidal left adjoint, and it lives under mod R. So mod R is R modules in spectra, and in particular, it's an HR linear functor. And so it makes a nice diagram commute, which is the one which kind of extends the diagram we've seen for geometric fixed points. So I can I use the square which I had before, and I kind of add another square, which is just I take 3 modules here, which I can write like that. And so in particular, I have this nice kind of geometric property. So if I take modular fixed points for the 3 module associated to some pointed G space, then what I get is again this 3 module associated to the fixed points. Okay. Another thing. So I can express modules of the constant Mackey functor in spectra for the Weyl group as some module category in G spectra, and the ring here is the right adjoint of geometric fixed points applied to HR underbar. So by this I mean the right adjoint of geometric fixed points. Apologies for not writing the right adjoint on the right hand side. Okay, and so under this equivalence, my functor is just the extension of scalars along a certain ring map, which is adjoint to this ring map here. So it's adjoint to the ring map I used to define my functor. You have properties which you kind of expect from geometric fixed points. I don't want to read out everything, but it's basically saying I can nest fixed points, and that's just taking fixed points for the whole thing up to a restriction. That's what this property 4 says. And property 5 says it's natural with respect to restriction along group homomorphisms. Okay. I guess I should also say I forgot to say this before. I define my functor for finite groups, but you can formally extend it to profinite groups, and then the fixed points you take are for pro-p subgroups. And yeah, it's actually surprisingly subtle to deal with the higher coherences, but yeah, it can be done. And so this functor exists in the profinite case as well. And so under this description I've mentioned before, the spectrum Mackey functor description of this module category, this modular fixed point functor is actually just a Left-Kahn extension along classical Brouwer quotients. So this is just Brouwer quotients on which restrict to finitely generated GR permutation modules. And what I get there is I send the free R module on a G set X, on a finite G set X, to the free R module on the fixed points. And I'll talk about a bit more about these permutation modules now. Right, and for that I need to talk about weight structures. And I guess most of you will probably have seen weight structures, but if you haven't, then you can think about T-structures, and you basically need to swap two directions. So in two of the axioms for a T-structure, you need to swap the direction, and then you get the notion of a weight structure. And these weight structures, they live on stable infinity categories, and it's essentially a pair of it's full subcategories, which is kind of a co-connective part and a connective part. And for example, if we think about complexes, then so for example, on the bounded homotopy category, weight structures correspond to stupid truncations, and T-structures correspond to good truncations. And so what we lose by swapping the directions in the two axioms is the functoriality of these decompositions. So we always have these weight decompositions, these cofiber sequences, but they're not functorial anymore. And so we can always intersect the connective part and the co-connective part and get the heart of a weight structure. And that's in general a full additive subcategory, but it's not a one category in general, as for T-structures. And there's a notion of a bounded weight structure, which is what you think it is, I guess. Okay, and the next statement I want to make is this one here. There is a bounded weight structure on the compact part of modules of the constant Mackey functor in G spectra, and it has weight hard the idempotent completion of finally generated permutation modules. So it's kind of the weight structure associated or generated by the following set. It's this one here. So I take the free modules associated to all open subgroups of G. I take the additive subcategory generated by that, and I take the idempotent completion, and I can generate a weight structure. And then, of course, I have to identify the heart, which is done by kind of taking the effective Burnside category, mapping it into this module category, and then arguing that I descend to the homotopy category, the R linearization, and the quotient by some cohomological ideal. And then in the end, the outcome is finally generated permutation modules. And then I have to show that's an equivalence. Okay. And I want to talk about functors between these weight structures. So the functor between these weight structures is such weight structures is weight exact if it preserves the connective part and the co-connective part. And maybe something that is less standard is this notion of weight conservative. And by that, I mean, if I map an object into the connective part, then it already comes from the connective part, and the same for the co-connective part. Okay, that's what I call weight conservative. And the existence of this weight structure, of this bounded weight structure, implies that there is an equivalence to the bounded homotopy category of the idempotent completion of finally generated GR permutation modules. And this builds on work of Zosnilo, which essentially says that stable infinity categories with bounded weight structures are the stable envelope of their heart. And in this case, my heart is a one category, and so the stable envelope is actually just this KB. Okay, and now I mentioned before that Balmer and Gallauer, to study the TT geometry of this derived category of permutation modules, have considered or defined these modular fixed point functors. So they've defined them as TT functors, and they naturally extend to infinity categories. And so what is this D perm GR? You can think about the incompletion of KB and finally generated permutation modules, or you take chain complexes of these permutation modules, and then the things which you mod out are maps, chain maps that are quasi-isomorphisms after taking fixed points for all subgroups of G. So it's kind of some more refined notion of the derived category. And so the statement here, which the theorem here is that under this equivalence, the equivariant modular fixed point functor I defined identifies with the one on derived permutation modules. And this is essentially proved as a statement about the heart. So you can reduce this to a statement about the heart, and this will also identify these functors as symmetric monoidal functors, in fact, because this whole work by Zosnilo about stable infinity categories with bounded weight structures has symmetric monoidal enhancements, which is work of Aoki. And so these functors identify because on the heart you essentially just have to check restrictions to subgroups and conjugations that kind of generate this is what you get, and there it's important which ring map you choose to define the equivariant modular fixed point functor. Okay, and another statement I will use later, I guess in 2 minutes, is the statement which Bachmann has proven in his thesis, and it's about a weight exact functor on stable infinity categories, equipped with weight structures, such that the weight structure on the source on C is bounded. And this functor is weight conservative, which is this notion I have above, if and only if the restriction to the heart detects sections and retractions. And so, yeah, what do I mean by that? I mean the following. So if F is a morphism in the heart of C, so I'll write weight heart and little w heart, such that f of f admits a retraction or respectively a section, then f admits one. Okay, and I will use this in a minute. I will now talk about the Picard group of this category of modules of the constant Mackey functor. And for that, I assume that R is a field of characteristic P. And I also assume that G is finite now. And later we will assume it's a P group. So I should furthermore say that this Picard group has been completely computed by Sam Miller using the language of representation theory. And there the invertible objects of KB, of finitely generated permutation modules, they're called endotrivial complexes. And yeah, so there is heavy representation theory, and it's a series of 3 papers where he computes this Picard group. And yeah, I'm gonna use some more topological methods. There will be one input from representation theory, but I think the functors play in nicely when you talk about this Picard group. Okay, so I'm gonna consider these modified modular fixed point functors, which are now on compact parts. And let me also say I can restrict to compact parts because this category is rigidly compactly generated, and invertible objects, which are kind of the elements of the Picard group, they're in particular dualizable, and dualizables and compacts agree, so I can restrict to compact parts. And so I take my functor on compact parts, and then I also compose with a restriction functor to the trivial group. And then I land in compact HK modules and spectra, and that is the same as bounded derived category or bounded homotopy category of finitely generated K modules or K vector spaces. Okay, and so the next statement is uses the statement I had before about weight conservativity, namely this family of modified modular fixed point functors is jointly weight conservative. And by the statement we had before, this is about detecting sections and retractions on the weight hearts. So this follows about a statement, follows from a statement about the weight hearts, which is the following one. So a map in perm GK, idempotent complete. This is also known as P permutation modules, is split injective, respectively split surjective, if and only if it is injective, respectively surjective, after taking Brouwer quotients for all P subgroups. Oh, sorry. Let me try that again. Does that work? I hope you can see that again. If not, please complain.
Yeah, it's okay.
Thank you. Okay, so yeah, I should say that by identifying my functor with the fixed point functor defined by Balmer and Gallauer, I identify it with Brouwer quotients on the heart and Brouwer quotients on these permutation modules, or I guess on the idempotent completion of those. It really takes a free module on the G set to the free module on the fixed points. And there's this criterion which is in the book by Linkelmann, and this implies the weight conservativity of this family. And I will explain how we use that. So we can now define this homomorphism here, which I call lambda, from the Picard group of the category I'm interested in into class functions. And so this is the group of integral class functions on P subgroups of G mod G. So I take conjugacy classes of P subgroups. That's what I mean by this notation, mod G. And we can map an element of the Picard group to the following class function. So it takes the class of a subgroup, of a P subgroup, to the integer for which the homotopy of this modified modular fixed point functor applied to X is isomorphic to K. So these modified modular fixed point functors, they are symmetric monoidal and they land in compact HK modules. And so the Picard group of that has elements just the shift of HK in an integer. So the integer shift of HK. And so I know that the homotopy will be isomorphic to K in a single degree. And that's the integer I take for this class function. Okay. And in fact, Balmer and Gallauer, I'm not using this at the moment for what I do now, but in fact, Balmer and Gallauer have shown that this family of functors is conservative, jointly conservative, and so the converse direction holds as well. So whenever we have a spectrum, maybe a compact spectrum, such that, it has to be compact, such that this holds. So the homotopy of these modified things is concentrated in a single degree, and it's isomorphic to K in that degree. Then the spectrum I started with was invertible. So this is what conservativity implies, but okay. And I can use the weight conservativity to show that when G is a P group, this homomorphism lambda is injective. And how do we do that? So we assume that this function we just defined is constant. So we assume it's constantly 0, which implies that this modified modular fixed point functor maps X into the weight heart of the target for all P subgroups. Conjugacy classes of P subgroups. And this implies that X itself must come from the weight heart because of the weight conservativity. So it comes from the weight heart, which is equivalent to the idempotent completion of this category. But when K is a field of characteristic P and G is a P group, this is already idempotent complete, which is also non-trivial, but I'm going to use this here. Okay. And so in fact, the only element of so the only so the only element of perm G K which has K dimension 1 is the free module on this one, on the point, so on the G set G mod G. And so I know that X must be equivalent to HK underbar already, which for which I'm using that I'm using modular fixed points for the trivial subgroup in this argument. Okay. And so from now on, we'll assume that G is a P group. And now there's a certain subgroup of the group of class functions coming in, which is this group of Borel-Smith class functions. And yeah, I'm giving you the definition here. I won't read it out, but it's essentially yeah, a definition about how class functions behave on certain subgroups, which have like certain quotients. So for example, I look at normal subgroups of a subgroup H, and then I have some assumption about the quotient, and then I have some condition on the class function. And they are defined for general finite groups. In that case, you would write CFB GP, and then you only yeah, so you only consider class functions on the P subgroups, and you can define these Borel-Smith conditions, but I won't write the P because I'm already assuming that I'm working with a P group. Okay. And so how does one show that one lands in this certain subgroup? Yeah, this is this input from representation theory I mentioned. There's this book homomorphism, and you can show that the precomposition of my map lambda with this book homomorphism is trivial. And Book and Yeltsin have shown that this homomorphism has precisely the kernel, the Borel-Smith class functions, and so you actually land in this kernel. I guess you could also show the Borel-Smith conditions by hand, but I didn't do that. And then we can give a nice argument for why this lambda, when I restrict my target to the Borel-Smith class functions, is surjective. And that's a nice commutative diagram. So we start with ROG, which is the real orthogonal representation ring associated to G. And there's a homomorphism into the Picard group of G spectra, which just takes a representation and maps it to its representation sphere. And yeah, I should say in general, this is neither injective nor surjective, but we don't need that because I want to map further. I want to take three functors, three module functors, and then I land in the Picard group of modules over the constant Mackey functor. So this is induced by the free module functor. And here I have Borel-Smith class functions, and I've got my homomorphism lambda. Okay, and now there's a homomorphism here, which is called dimension homomorphism, and it sends a representation V, real orthogonal representation, to the following class function. It takes the class of H to the real dimension of the fixed points of the representation. Okay, and it's work of Tom Dieck that this is surjective, this homomorphism here. And this builds on lots of things, that this is surjective. So first of all, that it actually lands in these class functions satisfying the Borel-Smith conditions. That builds on work on fixed points of GCW complexes, which are FP cohomology spheres, which is also work of Smith and Borel. And then the surjectivity is proved by Tom Dieck using dimension functions of orthogonal representations. And this is already builds on work by Attia and Tal and Sayre on Adams operations on ROG. So I went into Tom Dieck's book and I tried to trace back all the attributions, and it wasn't easy because there's a lot which feeds into this. But I hope I mentioned all the right names for the attributions. And okay, I guess this is commutative, and then my homomorphism lambda is surjective as well. And what I can also do is I can formally extend this result to pro-P subgroups. Yeah, this is kind of relatively immediate. And I should also say that for general finite G, Miller has shown the following. So I should say this is work by Sam K. Miller. The Picard group of this, or I guess in his language, the group of endotrivial complexes is given by these class functions, Borel-Smith class functions, and P subgroups, but you also get another factor, namely you get characters, like that. And this is essentially shown by restricting to a solo P subgroup, but yeah, there's also there's a fair amount of work which goes into this for general finite groups, and yeah, this can be done. Okay, yeah, thank you for your attention. Thank you for listening.
Thank you, Yorick. Let's all give the speaker a round of applause now. Right, so if you have any questions, please ask them. Can you, I mean, do your methods also imply some computational results for the, I don't know, the Picard groups of spectral functors?
I haven't considered this, but yeah, I guess you need to produce some functors in that case, but yeah, I mean, do you mean just G spectra spectrum functors? Because the Picard group of G spectra is like, yeah, I mean, there are some descriptions of that, I think. But yeah, I think
Or like
there's
EN
more
locally?
to be said about like general categories of the spectrum functor kind. And yeah, maybe you can do things using similarly defined functors, but I haven't done this yet.
Okay. Any other questions?
Does the last theorem you have there, you're giving a new proof of something, of this algebraic result about endotrivial modules, right? And how different is it from the existing proofs? I guess I've heard talks by John Carlson and people like this as they were working on this problem. Is the input from group theory or representation theory the same, or is it different, or how is it different?
Yeah, so I think so. For example, this last statement about surjectivity, this is kind of something topological, which I'm not exactly sure, but I think they have not been using that. There are other things which are very analogous to the representation theoretic case, and also this representation theoretic input I mentioned. So, for example, this Miller uses this input as well. So Miller uses this book homomorphism as well. And so some of the statements Miller uses have like direct topological analogues, and I'm using them as well. But yeah, so I think this last thing is kind of has not really been used. And yeah, and also I think it's nice to have this family of functors in this way. So this weight conservativity statement, for example, because it kind of translates something from representation theory into like genuine equivariance, which you can phrase in a very clean way, I think.
Yeah, it seems like, I mean, obviously, Tom Deek would have been interested in the topological applications and degree theory and all that sort of stuff. But right, it just seems like this algebraic result that this map on the top there is surjective. I mean, my goodness, this has to have if it's true, it has to have some sort of straightforward group theoretic proof somehow.
Yeah,
It would seem to me. I'd be really shocked if it didn't, but anyway.
yeah, I agree. But
I mean, one would think one would prove it using algebra and then group theory, right? Yeah.
mhm. Yeah, I agree.
Curious. Curious. Okay.
Thank you, Nick. Any other questions? The results from earlier that you mentioned, I mean, your results from earlier about the existence of a bounded weight structure, where you know what the heart is exactly, those kinds of results, I mean, I guess this is a different case. I mean, the theorem that is on the screen right now, I mean, those kinds of results don't usually have any bearing, right, on computing the Picard group, or do they?
They don't have what?
Do they have any bearing on computing the Picard group?
Ah,
I would have thought they are very different realms.
well, I mean, yeah, well, as I just said, I mean, to some extent, this weight structure is kind of the correct framework to phrase some things which directly relate to the Picard group. So yeah, I spent a while trying to think about what is this like kind of what Miller does. How do you actually make these things like inherently topological? And I think this weight structure is kind of the correct framework to do that. So yeah, that's kind of the way I think about it. So
Okay.
it's phrasing things from representation theory in the equivariant setting.
Thank you. Any more questions, anybody? Well, if not, let's thank Yorick once again. We don't have a talk next week. The week after next week, we have Victor Sonia. Bye-bye.